This video is going to give you an overview about the topics that you are going to learn in Chapter 2. Chapter 2 is talking about limits. What do we really mean when we say that a limit of a function at a point? Well, an informal way of describing a limit of a function at a point is better given geometrically illustrated using the following figure. Now, as it's evident from the following figure, once you are approaching or getting very close to the point A on the x-axis, then you will notice that for this point that is approaching A in the x-axis, the value of the function at this point is getting closer and closer to certain value on the y-axis, which is L. Now, if this is true, then we say that the limit exists and it's equal to the value L. Now, when we are saying that we are approaching or getting close to the point A on the x-axis, from where actually we are saying that we are approaching A? Is it from right or from left? Well, we mean from both directions. So first, once we are getting closer to A from the left, that means all the points axis that's approaching A is going to have a value less than A. Then the value of the function at these points is going to approach and getting closer on the y-axis to the value L. Then we could say that the limit when x approaching A from the left for f of x is equal to L. Now, if you are approaching A from the right on the x-axis, so that means all these points which is approaching A is going to have a value greater than or having a value more than A. Then the value of the function for these points is going to approach and getting closer to the value L on the y-axis. Then we could say that one-sided limit from the right, limit when x goes to A from the right for f of x is equal to L. Now, if the one-sided limit, the limit from the left and from the limit from the right is equal to the same value L, then we could say that the limit exists and it's equal to the value L. So limit when x approaching A for f of x is equal to L. Where here, since we didn't use any sign plus or minus, that means from both directions, from left and from right. Notice here that your function is not defined at the point A, but the limit exists. Now, if you redefine your function again to be continuous rather than discontinuous at the point A, you will notice that is the value of your function and the point A is going to be just equivalent to the value L, which is your limit. This is a very powerful result for continuous function. For continuous function, if you are interested to find what is the limit at certain point where your function is going to be continuous, it simply is going to be equivalent to the value of your function evaluated at this point. Now, some examples of these continuous functions is like trigonometric functions, sine and cosine, an exponential function like e to the power x, and logarithmic function like ln of x. Also, in this chapter you are going to learn some theorem and rules that's going to simplify the calculation and the computations that's involving the limits. One of these theorem is the following. If you know what is the limit when x approaches A for f of x and the limit when x approaching A for g of x, both of these limits exist, then the limit when x approaching A for f of x plus or minus g of x is just equivalent to the limit when x approaching A for f of x plus or minus limit when x approaching A for g of x. Also, for the product of the function, limit when x approaching A for f of x times g of x is just equivalent to limit when x approaching A for f of x times limit when x approaching A for g of x. Also, for the quotient, limit when x approaching A for f of x divided by g of x is equal to limit when x approaching A for f of x divided by the limit when x approaching A for g of x. Here for the quotient, be careful that the limit when x approaching A for g of x is not equivalent to 0. Do you think that the limit is always going to exist? Well, the answer is no. It's not always the limit exists. One of the cases that the limit does not exist is that if the one-sided limit exists, but they are differs. For example, the limit when x approaching a from the right for f of x is equal to some real number p, and the limit when x approaching a from the left for f of x is equal to some another number, real number c. Now, if p and c are different real numbers, then that means the limit does not exist. So if the one-sided limit exists but they are different, then we say in general the limit does not exist. Also, another case for the limit does not exist is that when we are approaching a vertical asymptote for the graph of your function. Look at the following figure. Now, part A of the following figure is having the graph of the function f of x is equal to 1 over x minus a. Now, this function have vertical asymptote at the line x is equal to a. Why is that? Well, first of all, your function is not defined at a. Secondly, that the limit does not exist whenever we are approaching a. How did we know that the limit does not exist? Well, look at the figure. When we are approaching a from left, you will notice that your function will decrease without any bound. When we are approaching a from right, your function is going to increase without any bound. In this case, we are going to say that the limit when x approaching a from the left for f of x is equal to minus infinity, and the limit when x approaching a from the right for f of x is equal to infinity. Now here, infinity and minus infinity is notation to denote that your function is increasing or decreasing without any bound. Infinity and minus infinity are not real numbers. They're just a notation to represent for you how your function is going to increase or decrease when we are approaching certain value. So that means the limit here does not exist. Also, another case when we are approaching a vertical asymptote is illustrated in the part B of the figure. Now here, the function that's given is f of x is equal to 1 over x minus a all squared. The graph here of your function is illustrated as follows. If we are approaching a from left or from right, in both cases you will find that your function is going to be increasing without any bound. Again here, the limit when we are approaching value a does not exist. This is not the only case when we are dealing with limits that's involving infinity. Also, we might be interested in what happened to your function when x goes to infinity or to minus infinity. What does it mean? Well, it means that in the Cartesian plane, we wanted to know what happened to your function if we are going far in the negative or far in the positive directions of the x-axis. What happened to your function? If it is approach certain value or a certain horizontal line, then we are saying that this horizontal line is going to represent for you a horizontal asymptote for your function. Okay, for example, the following figure is going to illustrate the case for horizontal asymptotes. Notice that when we are going far to the right in the x-axis, you will notice that the curve of your function is approaching the horizontal line y is equal L2. Now here, the line y is equal to L2 is going to present to be as a horizontal asymptote for your function. Also, if we go far in the left direction of the x-axis, you will notice that the curve of your function is approaching the horizontal line y is equal L1. Here, y equal L1 is going to be another horizontal asymptote for your function. Notice that in this case that L1 and L2 is different values, but it's not necessarily. Sometimes we have some cases where in both directions, if we go far in the positive direction or in the negative direction of your x-axis, we will approach the same horizontal line. So this horizontal line is going to be your horizontal asymptote for your function. Or sometimes only from one of the directions, going far in the positive direction or far in the negative direction of your x-axis, your function will approach certain value. And then this value is going to behave like your horizontal asymptote for the function. Determine all vertical and horizontal asymptotes, if there are any, of the graph of the function f of x is equal to x plus 3 divided by the square root of x squared minus 1. Keep a note of this question and try to answer it once you finish these two topics in chapter 2. If you fail to answer this question, then go back to your chapter and read it again. Now, we've been talking about the limits and the geometric interpretation of that, and we presented in an informal way. But if we wanted really to prove or to show that the limit exists, we need to give a formal definition for the limit. The definition says, suppose a function f is defined everywhere on an open interval except possibly at a number a in the interval. Then the limit when x approaching a for f of x is equal to L means that for every epsilon greater than 0, there exists a number delta greater than 0 such that the absolute value of f of x minus L is going to be less than epsilon whenever the absolute value of x minus a is greater than 0 less than delta. What does this definition really mean? Well, now look at the following figure. Now, if you wanted to define or describe basically what does this definition means, then we wanted to take an interval, a small interval around the point A on the x-axis, such that we wanted to measure how close we are to the point A. Because before we were saying that we are approaching or getting close to the value A on the x-axis. But we didn't really measure or define what do we mean or when do we state that we are close or far from the point A itself. Now here in this definition he will give you some measure or some reference point as to say that when you are close or not close to the point A on the x-axis, and the same thing for the point L on the y-axis. Now here the reference point that we are going to take is the delta. So it's a positive small number, delta, greater than 0. And now we are going to say that take the interval around the A, such that the endpoint of this interval is going to be A minus delta and A plus delta. Now if you're taking any point in this interval, is going to be its distance from the number A is less than delta. That's why we are saying that the absolute value of x minus A is less than delta if you are choosing this number that's close to A to be x. Now, according to the definition, the value of your function at this point x is going to be within a distance from the value L on the y-axis is less than epsilon. And that is what you are going to see on the figure. You will see that f of x is going to be within a distance from L is less than epsilon. And that is the meaning of the absolute value of f of x minus L is less than epsilon. Now, if you are able to do this, then you proved that your limit exists. That is the most basic material that you expected to get in chapter 2. So, good luck with this chapter. I hope you are going to get good result and succeed to understand this chapter.